In this video, we're going to be covering the last topic of carbohydrate chemistry, which is the discussion of disaccharides and by extension polysaccharides. So let's just review. Disaccharides are carbohydrates comprised of two monosaccharide units, and there are several types of disaccharides. So before we get into anything else, before we get into the reactions of disaccharides, let's first review glycoside formation from the reactions of monosaccharides. So if we review the mechanism, if we review the reaction here, remember that glycoside formation just refers to the formation of an alkoxy group, or refers to the formation of an alkoxy group that's attached to the specifically only the anomeric carbon, which in most cases is usually C1, while the other hydroxyl groups remain unaffected. So we can see here that generally the only carbon that's really affected in this entire reaction is this carbon, in most cases. The other hydroxyl groups tend to remain unaffected during glycoside formation. Okay, we're going to see a common theme with that with the formation of disaccharides. Okay, so let's just review the mechanism of glycoside formation. So remember that there's a proton transfer from the acid is deprotonated, which protonates the hydroxyl group of carbon 1, or the anomeric carbon. The anomeric carbon is protonated, forming a hydronium ion, and this makes it a good leaving group, right? So what we're left with is the formation of a resonance stabilized carbocation, and we'll see that there is a nucleophilic attack on the anomeric carbon, which can either be in which the anomeric carbon could be nucleophilically attacked from the top or from the bottom, as I show here in this schematic. Right. Once that happens, we have the formation of an oxonium ion, or an alkoxy group that's currently protonated. And what needs to happen is a second proton transfer, where the oxonium ion is deprotonated by, in this drawing here, a water molecule, but it could also be from a deprotonated acid, where the acid becomes reprotonated, and what we're left with are two and what results are two stereoisomers. Okay. With the idea of glycoside formation in mind, let's go through disaccharide synthesis reactions. So from the reactions we saw with glycoside formation, if disaccharides are formed via glycoside formation, then the reaction conditions can be considered the same as typical glycoside reactions. So we can see here that in the presence of two sugars and an acid, under acidic conditions, we can see that reactions go to form two stereoisomer products. One, which in the case of two glucose molecules reacting, we see the formation of Cellobiose and Maltose. Let's take a closer look at each of these stereoisomers. So we can see here that Cellobiose in it, under IUPAC nomenclature, we can see that its formal name is 4-O, O for the oxygen bond that's formed between the two monosaccharides. 4-O-beta D-glucopyranosol, beta D-glucose. So we can see here that beta refers to the fact that both the substituent for carbon 1 and the substituent for carbon 5 are both on the same side of the ring, right? That's just what this indicates. Okay, let's keep this substantial difference in mind, because the name change, there's a very subtle difference that you'll see with maltose. So keep this in mind, beta D-glucopyranosyl, which just refers to the first monosaccharide of a disaccharide. Now, if we take a look at maltose, you can see that maltose's IUPAC name is 4-O-alpha D-glucopyranosyl beta D-glucose. So we can see here that the subtle name change occurs here, where we can see that the substituent for carbon 1 and the substituent for carbon 5 are on opposite sides of the ring, hence the term alpha. Okay, so that's essentially the basics of glycoside or disaccharide formation or disaccharide synthesis. So let's go through the IUPAC nomenclature for disaccharides. So we can see here, as I've already described, that for maltose, we assume that the IUPAC nomenclature is 1,4,0 alpha D-glucopyranosyl beta D-glucose. So let's get into the specifics of let's break down the specifics of the name of the IUPAC nomenclature here for this disaccharide. So I've labeled here in green monosaccharide 1, and we can see that monosaccharide 1 is already in the alpha configuration, is shown in the alpha configuration, while monosaccharide 2 is in the beta configuration, where both the substituents of carbon 1 and carbon 5 are on the same side of the ring. And we can see that in the IUPAC nomenclature, monosaccharide 1 is believed to be the substituent, hence the name alpha D-glucopyranosyl, nosyl indicating that it could be, that it's suggesting that monosaccharide 1 is the substituent, while beta D-glucose is the main monosaccharide in the disaccharide. So in purple, what I've shown here, the beginning of this name, indicates the specific carbons. So the numbering here for the linkage indicates the specific carbons participating in the glycoside linkage. So the anomeric carbon, or C1, will almost always, I say always in the description here because that's usually what happens, right? In glycosidic linkages, it's usually a 1,4 linkage between units, right? But this won't always be the case, as we'll see later. So the anomeric carbon C1 will always be a participant in glycosidic linkage. Now, in green, in green text, we can see here that the name indicates that the pyranose ring is acting as the glycoside. In essence, its anomeric carbon is participating in a glycosidic linkage, right? And we can see that this portion of the name also indicates that the stereo configuration of C1 and C5. So we can see that the stereo configuration of C1 and C5 are alpha. Remember that alpha equals alpha suggests the positioning of the substituents to be trans to each other. In essence, the substituents are facing in opposite directions. Whereas cis substituents are facing in the same direction, and this is what we call beta, right? Just something to keep in mind as we go through all the other examples of disaccharides here, okay? So with this in mind, let's go through the actual mechanism. So the mechanism is just the same as you would see for any other glycoside. We can see here that there's a proton transfer followed by the loss of a leaving group, which forms the resonance stabilized carbocation. A nucleophilic attack occurs either from the top or the bottom. And we can see that the nucleophile here is the second monosaccharide unit, right? And we can see here that a proton transfer is needed for this reaction to go to completion. And what we're left with are 2 stereoisomers. Now let's just verify. Cellobiose 1,4,O beta, which is correct because the substituents for carbon 1 of the first monosaccharide and the substituent for carbon 5 are in the same side, so this is correct. Beta D-glucopyranosyl, beta D-glucose, that is correct. And then maltose 1,4 oxygen linkage, and yes, this is also correct because the substituent for carbon 1 and the substituent for carbon 5 are on opposite sides of the ring, so we consider this to be alpha D-glucopyranosyl beta D-glucose. This is correct. Just reviewing once more the reaction conditions for any glycoside formation reaction, is that the reaction conditions must be that the reaction itself must be acid catalyzed, the nucleophilic attack occurs from a variable alcohol, and upon isolation, under nucleophilic attack occurs from a variable alcohol, which in this case is monosaccharides. Because, as we remember before, monosaccharides are polyhydroxylated ketones or aldehydes. But the key word in that description of a monosaccharide is polyhydroxylated. Right. Now, upon isolation, the glycosides formed can be stabilized under neutral or basic conditions. Okay. Now, there's several. I want to discuss the properties of several disaccharides. Let's start with maltose. So, maltose, as we've already established, is a 1,4-alpha glycoside because the substituent of carbon 1 and the substituent of carbon 5 are on opposite sides of the ring. Right? The pyranose ring that isn't a glycoside, so monosaccharide 2 in this case, right? Monosaccharide 2 contains an anomeric hydroxyl group, and therefore its anomeric carbon is a hemiacetal capable of mutarotation in its open chain form and can switch between 2 anomeric forms. So, because of this property, because maltose contains an aldehydic hydrogen atom, or because it exhibits mutarotation, maltose is capable of becoming is capable of acting as a reducing sugar, meaning it is capable of reducing a compound in the process of becoming oxidized. But before we get into all that, let's go through the special property of maltose acting as a let's go through the special property of maltose acting exhibiting mutarotation. So we can see here that this is 1,4-alpha 1,4-oxygen alpha D-glucopyranosyl beta D-glucose, or maltose, right? Now remember that the second monosaccharide, or monosaccharide 2, is capable of mutarotation, right, in its open chain form. So this is the same this is maltose, but in its open chain form, more specifically monosaccharide 2. When it rotates, we can see that what forms is a change in the configuration, and now we can see that the configuration of the substituents has changed, where the substituent for carbon 1 is facing one side of the ring, while the substituent for carbon 5 is facing the other side of the ring. And we can see here that the configuration of the second monosaccharide is now alpha. So we can see here the change, where previously the second monosaccharide had a configuration of beta, but here it becomes alpha due to mutarotation. And what we're left with is 1,4-oxygen alpha D-glucopyranosyl alpha D-glucose. Okay? That's essentially the whole description of what happens here. Several monosaccharides follow this too, such as Cellobiose. Now, Cellobiose is a 1,4-beta glycoside, and the pyranose ring that isn't a glycoside contains an anomeric hydroxyl group, and therefore its anomeric carbon is also a hemiacetal capable of mutarotation. So, because of this property, Cellobiose is also a reducing sugar. So we can see here the same thing like we did with maltose. So Cellobiose, the second monosaccharide, will open and exhibit mutarotation because of the anomeric carbon, and it will rotate to switch to the alpha configuration, forming alpha D glucose. So what we're left with is a different variation, a stereoisomer of Cellobiose, where the second monosaccharide is in the alpha configuration, shown here in the name 1,4-oxygen beta D-glucopyranosyl alpha D glucose. Okay. Now, lactose is a very different. It's different from the previous disaccharides. Now take a notice here between maltose and Cellobiose, where the only difference between the two between the two disaccharides is the configuration. So the spatial configuration. So you can see here that the configuration for maltose is alpha, while the configuration for Cellobiose is beta, and that's why we assign these names to these, because of the difference in their spatial configuration. Okay, but lactose is different because lactose is comprised of two different monosaccharides. They're comprised of glucose, which is one monosaccharide, and galactose, another monosaccharide. And the relationship between the two monosaccharides is that glucose and galactose are diastereomers. The configuration only differs at C4, right? Or the C4, more specifically the hydroxyl group. Okay. So, we could see here that galactose has a hydroxyl group in the axial position, right? This hydroxyl group is in the axial position. Compare that to glucose, where the hydroxyl group is in the equatorial position, and that's why we refer to these as diastereomers, since the spatial configuration of only one carbon chain is different. At least it's what it looks like to me. This may be incorrect, but feel free to correct me if I'm wrong on this. It's similar to, so lactose is similar to Cellobiose in the sense that it's a 1,4-beta glycoside, but yeah, that's pretty much the only similarity they have. The pyranose ring that isn't a glycoside contains an anomeric hydroxyl group, and therefore its anomeric carbon is a hemiacetal capable of mutarotation in its open chain form and can switch between the two anomeric forms. So because of this property, Cellobiose is a reducing, not Cellobiose, I don't know, it's lactose. Lactose is a reducing sugar. So lactose, or 1,4-oxygen beta D galactopyranosyl beta D glucose. So we're already given specific details about the name here. So we can see here, let's break this up into two bits here. This is monosaccharide 1. This is monosaccharide 2. We can see here that the second monosaccharide is in the beta configuration, because the substituent of carbon 1 and carbon 5 are on the same side of the ring, whereas the same thing occurs with beta galactose, beta D-galactopyranose, with the beta D-galactopyranosyl group, where the substituent of carbon 5, carbon 1 are on the same side of the ring. Okay, so that's essentially what the entire name is referring to. So when the ring of the second monosaccharide opens up, we get we get the same thing in its open chain form, but when it undergoes mutarotation, the configuration of glucose, the stereo configuration of glucose changes, forming alpha D glucose. Okay, and then what we're left with is 1,4 oxygen beta D galactopyranosyl alpha D glucose. Okay. Lastly, the last disaccharide that we have is sucrose. Now, sucrose is completely different from the previous three disaccharides that I've reviewed, because what we have here is sucrose, which is comprised of two different monosaccharides: glucose, which is an aldose, and fructose, which is a ketose. And the difference between these two monosaccharides is relatively obvious, because they are structural or constitutional isomers of each other. Okay? They're structural isomers, meaning that how the atoms are connected between each constituent of the molecule are different compared between glucose and fructose. So this is a very peculiar formation of a disaccharide. So let's just go through the synthesis of sucrose. Now, it's important to note that the formation that the glycosidic linkage here is very different from the previous two. We can see here that the linkage occurs between carbon 1 and carbon 2, so we get a 1,2. This is a 1,2 glycosidic linkage. You can't say that this is a 1,5 glycosidic linkage, and that would technically be incorrect, because what we see here is essentially the flipping of a ring. Okay, so if I show you the mechanism, this should perhaps clear things up. So we can see here that the hydroxyl group of glucose is protonated by an acid, followed by the loss of the leaving group, which is a hydronium ion, forming the resonance stabilized carbocation that we typically see. However, we can see here that before the nucleophilic attack occurs, before fructose nucleophilically attacks the glucose molecule, we can see here that the fructose molecule literally flips, as I show here in this diagram, so that carbon 2 can act as the appropriate nucleophile, or the oxygen at the hydroxyl group on carbon 2 can appropriately nucleophilically attack the glucose molecule. And it's important to note here that when the nucleophilic attack occurs, what only forms is an alpha linkage, not a beta linkage. So once this forms, we have one more proton transfer, and what we're left with is 1,2 oxygen alpha D glucopyranosyl alpha fructose. That's essentially the entire mechanism here. Yeah. That's essentially it. I don't think there's much else to cover. And the reason why I wanted to clarify that this is not the correct way to represent the molecule or to accurately depict the molecule is because remember that that an alkoxy that an ether group is formed upon nucleophilic attack, and that's why it didn't make any sense to me why that's why I realized that the mechanism doesn't make sense if the attack was to occur at carbon 5 of the fructose group, or with fructose using carbon 5 as the nucleophile. It wouldn't make any sense. So that's why I had to logically reason that carbon 2 would actually be the appropriate the carbon 2's hydroxyl group would be the appropriate nucleophile. Okay, let's just review that one more time. Yeah, I've even colored the hydroxyl group of carbon 2 to be purple to properly indicate that the ether group that formed was thanks to fructose. And that's usually a common pattern that we'll see with a lot of reactions involving glycoside formation, is that the ether group forms thanks to the presence of the alcohol, not the first monosaccharide. Okay, it's usually thanks to the second monosaccharide that acts as the nucleophile that forms the ether group. Okay, and the very last part of our discussion here that I want to include here is the discussion of polysaccharides. So polysaccharides are polymers made up of repeating units, or monosaccharides, linked together by glycosidic bonds. In most cases, usually a 1,4 glycosidic linkage. But in the context of polysaccharide hydrolysis, where polysaccharides can be hydrolyzed to form smaller units of polysaccharides and eventually leading to disaccharides and then monosaccharides. Polysaccharides can be considered precursors to disaccharides. So cellulose is a type of polysaccharide that is likely a precursor to cellobiose, right? Now into the specific details of cellulose. Cellulose is a polymer linked by 1,4 beta-glycosidic bonds, making it resistant to hydrolysis for human small intestinal enzymes, and therefore cellulose has no nutritional value because humans lack the small intestine of the human lacks enzymes necessary to break cellulose down into cellulobiose, or into smaller units, right? Cellulose is comprised of beta-D-glucopyranose units, and strands of this polymer interact via hydrogen bonds, providing structural rigidity for trees and plants. Okay, now a derivative of cellulose is chitin, which has the same beta 1,4 linkage as cellulose and cellulobiose by extension, but chitin differs in the sense that its units are comprised of amino sugars, right? It's an amino sugar polymer with N-acetyl amino sugars as the repeating units. So amino sugars are carbohydrate derivatives in which a hydroxyl group is replaced with an amino or amide group. So in the case of chitin, we can see here that the amino or amide group is this N-acetyl amino group. Okay. This is what chitin is. You can see here that there's the familiar 1,4 beta linkage. 1,4 beta linkage. And you can see here the amino, the acetyl group, the amino acetyl group, okay? And acetyl amino group. Next up, we have starch, and starch comes in two forms. There's starch amylose and starch amylopectin, okay? Now, amylose is a polymer linked by 1,4 alpha glycosidic bonds, making it ideal for hydrolysis by human small intestinal enzymes, because there does exist enzymes for the breakdown of starch or amylose, and the enzyme for this is called amylase. Okay, so amylose is comprised of alpha D glucopyranose units indicated by the alpha configuration, right? You can see the familiar alpha configuration where the substituent for carbon 5 and the substituent for carbon 1 are on opposite sides of the ring, right? And this chain repeats. Okay, so the polymer is linked by 1,4 alpha glycosidic bonds, making it ideal for hydrolysis by human small intestinal enzymes. It's comprised of alpha D glucopyranose units, and one key trait of amylose is that it's insoluble in cold water. Okay. On the other hand, we have amylopectin, right? It's also a polymer linked by 1,4 alpha glycosidic bonds, which also makes it ideal for hydrolysis by human small intestinal enzymes. It's comprised of alpha D glucopyranose units, but the difference between amylose and amylopectin is that it's soluble. And amylopectin is soluble in cold water, while amylose is insoluble in cold water. Okay. And amylopectin has a special property where it contains 1,6 glycosidic bonds that allow branches of alpha glycoside units to form every 25 glucose units approximately. So we can see here that another key distinguishing feature of amylopectin is that it has a 1,6 glycosidic linkage, right? You can see the glycosidic linkage formed between these two carbon atoms, right? I didn't cover the last polysaccharide, but you can just make an assumption, a general assumption, that it would act similar to amylopectin, which is glycogen. And glycogen, as we know, is a polymer that's found in the in muscular tissue, generally found in muscular tissue of humans. And glycogen essentially is relatively more branched than starch or amylopectin. Okay.